Hello, Honors Pre-Calculus. This is section 10.8, polar graphs. So we're going to start by looking at special polar graphs. You were supposed to graph a bunch of different equations and just kind of see what they look like, and some of them fit into categories. And it does say at the top here that a lot of these are easier to graph in polar form, because when we put them in rectangular form with x's and y's, it's just more complicated. And they have an example of just a circle. So the first category are called limesons. And for this category, you will see that the a and the b values, which are just numbers, are either adding or subtracting with cosine or with sine. A and b both have to be greater than 0 for this to work. There's a few different graphs we can get from it. The first one would be if A over B is less than 1, we would have a limason with an inner loop, a limason with a loop. If A over B equals 1, we get a cardioid, which is heart-shaped, so they call it a cardioid. A dimpled limason would be if A divided by B is somewhere in between 1 and 2. And if A over B is greater than or equal to 2, we get a convex limason. There are curves called rose curves, and those would be the ones that look like flowers. We did quite a few of those. And what you should have self-discovered and discussed in the discussion board would be n petals if n is odd, and 2 n petals if n is even, as long as n is greater than or equal to 2. And here we've got different pictures of the rose curves, and you can see the n value is in front of the theta, the multi-angle. And then the last category is circles and lemniscates. So the circles, we could have a cosine theta or a sine theta, and that's going to determine where the circle sits. Or lemniscates start with an r squared and have a sine 2 theta or a cosine 2 theta in their equation. We're going to graph these, and we can make it a little bit easier on ourselves by using shortcuts. Like if we know there's symmetry, then we can just find a few points rather than finding all of them. So there's 3 tests for symmetry. The first one would be to replace r theta by either pi minus theta or negative r negative theta. Replace r theta by, the polar. I'm not following along very well. Number 2 would be symmetry on the polar axis, and that would be replacing r theta by either r negative theta or negative r pi minus theta. Or you can have symmetry about the pole, and that would be replace r theta by pi plus theta or negative r theta. And here's 3 examples of what each of those would look like. The first one would be symmetry with respect to the line theta equals pi over 2. So here's that line, theta equals pi over 2, and you can see that these 2 pieces have symmetry. The next one would be the polar axis. Remember, this is the polar axis right here. And then the third one would be the pole, and you can see this one's kind of like a 180-degree rotation. So graphing a polar equation by point plotting. I'm not going to actually do the point plotting because you did a lot of that already. So I'm just going to talk about the symmetry. So to test symmetry for this, we'll use those 3 examples. The first one is the line pi over 2. Or theta equals pi over 2, I should say. And to test that, I'm going to replace in the equation, I'm going to actually use the second suggestion because I thought this way was easier when I tried it earlier. And that could be just something that you try and figure out. So I'm going to replace r with negative r. And then I'm going to replace theta with negative theta. And then what I'm going to do is I'm going to use our identities that say sine of negative theta is the same thing as negative sine theta. And if they're both negative, I could divide both sides by -1, and I would get r equals 4 sine theta. And you can see that that's the original question. So we do have symmetry above or about the pi/2 line. And let's say I tested the polar axis, which we will replace with r and then negative theta. So if I take the same equation and I put in just r, and then I use negative theta, well, that's a lot like the one above it, except for I'm going to have r equals -4 sine theta. So that one definitely does not have symmetry. And we can see in the picture too, but I want to just show you me checking the testing the symmetry. And then 3, we are going to use, oh, this is the pole itself. And we're going to use -r theta. So I put in -r, we would have 4 sine theta, and there's no way to change this to make those equivalent, so it is not symmetric on number 3 either. So it only has symmetry on theta equals pi/2, which is this line right here. And then as you find some of these points, maybe you find these points, then you can automatically go ahead and reflect those. You have less to do. So here's another example of symmetry. So we're going to test our symmetry. I'm not going to do all the plotting because you did a lot of plotting already. So let's test the first one, which is theta equals pi/2. And so I'm going to put in -r, negative theta. So I put it, oh, that's too small. I'm putting in -r, negative theta. And so I get -r equals 3 plus. Now, when I use my identity from chapter 5 for cosine negative theta, the identity says just cosine theta. So we can see that these are not the same as the original. So now I'm going to try the polar axis. And so for the polar axis, I'm going to use r negative theta. When I plug that in, I will get r equals 3 plus 2 cosine theta using my identity from chapter 5, and that is the original. And then the last one is we're going to try the pole. We'll replace -r theta. And there's no way to make that equivalent. So that does not have symmetry about the pole. So really all you have to do is find a few points. And from there, it's symmetric above that pole or around that polar axis. Now, sometimes the tests of symmetry are not sufficient to guarantee symmetry. So here's an example. It's called the spiral of Archimedes. The equation is r equals theta plus 2 pi. If you use the tests, they're going to fail. But when you look at the graph, it does have symmetry that with that pi/2. It does have that symmetry. So you can't 100% guarantee symmetry from those tests. It's just helpful if it does have symmetry to save you some time. And then another thing that is discussed here is anytime we have a graph of r equals some function with sine theta in it, it's going to be symmetric with the respect to the line theta equals pi over 2. And then if we have the graph g of cosine theta, which means we have some function of cosine theta, it will have it will have symmetry with respect to the polar axis. Couple other things that might help you graph these quicker would be just knowing the maxes of the maximum values of sine and cosine, like the sine graphs and the cosine graphs. Just when we were originally graphing those way back in chapter 4, sine had like a maximum value of 1, and that would be at pi over 2. And then it had that negative 1 value at 3 pi over 2. And then cosine had a maximum value of 1 at 0 and of negative 1 at pi. And just knowing that's going to help us because, for example, right here, when we had 4 sine theta, we know that the radius is 4. Well, the maximum is going to occur at pi over 2 because that's where sine typically has a maximum. Another thing that you can use would be zeros, where like sine of theta, theta is equal to 0 at 0 and pi. And then cosine of theta is equal to 0 at pi over 2 and 3 pi over 2. So here's an example of sketching a polar graph. The sketch is there. I just want to talk about just going kind of like through the steps to kind of shortcut it so you don't have to plot every single point from hand or like by plugging in every single point. So we're going to sketch the graph of r equals 1 minus 2 cosine theta. So we're going to talk about symmetry. And we notice that it's cosine theta. Now I can go ahead and test the symmetry. Or I can use up here where it says that we're going to have symmetry with respect to the polar axis. And then we'll talk about the maximum values of r. So r is equal to 1 minus 2 cosine theta. Now I know cosine theta is usually at a max at 0 or pi. That pi would be negative. So if I put 0 in there, I'm going to get 1 minus 2 times 1, which is actually negative 1. And then if I put pi in there, I'm going to get 1 minus 2 times negative 1, which is 3. So we have a maximum value of 3. And that's going to occur when theta equals pi. And then the 0 of r, if I make r equal to 0, 1 minus 2 cosine theta. Oops. Let's solve that. How about I move that one over? I'll get 2 cosine theta equals 1. We'll divide both sides by 2. I'm going to get cosine theta equals 1/2. And then I'm going to do inverse cosine of 1/2. And that's going to give me theta equals, and that'll be at pi over 3. So we know that there's a 0 at pi over 3. We know that the maximum occurs at pi equals theta. So you can see at pi equals theta, we've got that maximum value of 3. We've got the minimum value, minimum value, yes, but it's the 0 of r. at pi over 3. So that one's a little harder to see because if it's at 0, it could really be at any angle at that point. Already plugged in 0 to find the answer to be -1. So you can see that point there. So all you need to do is find just a few more points and plot those. And then we can use symmetry to reflect it in the polar axis to find the rest of it. And then this here, right here says, note how the negative R values determine the inner loop of the graph in the figure. And you saw that when we did like the -1 R value, that's on that inner loop. So here's another one, example 4, sketching the graph of 2 cosine 3 theta. So for this one, the symmetry is in the polar axis because it's the cosine. Now for the maximum value for this one is a teeny little bit different. 3 theta is theta here, 3 theta. So the maximum value of this would be at like 0. It would be another time around at 2 pi, and it would be 3 pi. So I went 3 times around because this right here is telling me to go around 3 times. Is telling me like how many cycles, how many periods we're going to go through. So I went around 3 times, and then what I'm going to do is I'm going to divide by 3. And so our maximum value is actually going for theta is actually going to be at 0 pi over 3, 2 pi over 3. Hold on, I think I messed up. Pi over 3. Oh, I forgot pi. I'm sorry. I forgot pi here. Okay, so it would be 0, pi over 3, 2 pi over 3, and then pi. And then that would be a value of 2 for this particular equation. Okay, and then the zeros, go ahead, divide by 2. And then I want to find where just cosine 3 theta is equal to 0, which is at like pi over 2 and 3 pi over 2. But since it's 3 theta, we're gonna go around 3 times. So I'm gonna go around a second time, and I'll be at 5 pi over 2. And then I'll be at I think we're just gonna stop there. Okay, sorry. And then you'll divide by 3, so we are going to get that theta is equal to pi over 6. And then divide by 3, that's going to cancel the 3 here, so pi over 2, and then 5 pi over 6. So that would be your zeros. Here's a table of values, and it looks like I forgot to put, oh no, I didn't forget, I forgot. I'm sorry. I didn't forget to put it. It's on the next page. There's a little paragraph that says, by plotting these points and using the specified symmetry and zeros maximum values, you can obtain the graph shown below. And this graph is called a rose curve. And each of the loops on the graph is a petal of the rose curve. So it says it when we were talking about rose curves on that back page here. I'm going to notice that there's 3 theta, which is going to tell me that there's 3 petals for this graph. So here it's just graphing it in order so you can actually see how to graph each of these between each section in which you graph in order. I wanted to like have an animation. I couldn't really find one, so we'll just look and see how the book graphs it. And you should have done that. I I think it was the very first one in the assignment. All right, example 5. Sketching a graph of r equals 3 cosine theta. So the type of curve, using our chart from the very first page, the special chart type of curve. And this would be one that has multiple angles right here. So this is going to be a rose. Oops. It says 2 theta right here. And our rose curve directions on that page say whatever that n value is, we're going to multiply it by 2. So we're going to do 2 times this n value here, that's the n, and we get there's going to be 4 petals. All right, so symmetry, because it is cosine, we're going to use that symmetry, the polar axis. Maximum value would be, typically is going to be, typically is going to be when cosine is 0. I'm going to say if 2 theta, cosine 2 theta over here, the maximum would be at 0 or pi. This is telling me I need 2 cycles, so I'm going to also say 2 pi and 3 pi. And then we're going to divide everything by 2. So my maximum value is going to be the number 3. R is going to equal 3. At thetas that are 0, pi over 2, pi, and then 3 pi over 2. And then let's see, set it equal to 0. Divide by 3. So that would be normally at pi over 2, 3 pi over 2. We're going to divide by 2. So the thetas, the zeros for theta would be at pi over 4, and then 3 pi over 4. So down here, we've got our maximum value at 0. We've got a 0 at pi over 4. Then we have a maximum value at pi over 2. We have a 0 at 3 pi over 4. We have a maximum value at pi. And I could have kept going because there were more cycles, but because we know that it has the symmetry in the polar axis, I didn't need to go past pi. So if I go past pi, it's just going to be symmetric. And then, excuse me, and then, okay. And then, oh yeah, and then you can see on the graph that it also does have symmetry at pi over 2, but it didn't necessarily help us because we didn't test that. And then it does have symmetry about the pole as well. We can rotate it 180 degrees. It's gonna match up as well. Okay, so sketching a lemniscate. So hint, type of curve for this one. Now we're going to look at the r squared equals 9 sine 2 theta, and that is in the section on the first page that talks about lemniscates. It's the only one that has r squared. Okay, and then the symmetry for this one, well, we see that maybe we don't see. The symmetry for this one, let me test. I test, yeah, so the sine test won't work because of the r squared. It won't work for that. So we're just going to test. And let's see, we could test. I got to look at my chart again. I'm sorry. So the first one I'm going to test is negative r, negative theta, and that is for that line pi over 2. So if I do negative r, I'm still going to get positive r squared equals 9 times sine 2, and then we're going to have negative theta here. Well, that's going to be a positive r squared, but that's going to be a negative on this side, so that one's not going to work. And then our next one, r negative theta. So if r squared, we're going to end up with the same thing over here. We're going to have a negative theta, and with sine, it changes the sign, so that's not going to match up either. And then the third one, I'm sorry, I didn't label which one this one. This is polar axis. And then if we have the pole, then we're going to test it with negative r theta. And then if we plug in negative r into r squared, we get positive r squared, and the theta on the other side is staying positive. So that one does work. So we've got symmetry with respect to the pole. Okay, I'm going to erase this stuff so I can have some space for writing. Okay. So looking at the special polar graph section right at the beginning, there's two different kinds of lemniscates, and one of them is the just figure 8 right here, and then the other one has the figure 8 lemniscate, figure 8, they rhyme, right here, and this one is the sine version. So this is the one that we're looking for. It also tells you this length right here is a, where the a value is, well, this right here, the 9 is a squared. So the a value for this one's going to either be plus or minus 3. And, if it's minus 3, we're going to go the other direction. Okay. And then also the maximum of sine is typically at pi over 2. So since this is a 2 sine, then our max is going to be at pi over 4. And so we either have ordered pairs of 3 pi over 4 or negative 3 pi over 4. And that's going to give you like this point here and this point down here. That's going to be the 3 pi over 4 and then the negative 3 pi over 4. Another thing to consider would be, let's see, because there's a square, let me put the square root in. It's down below, but if I solve this for r, then we're going to get plus minus 3 square root sine 2 theta. And because we have a square root when it's solved for r, sine 2 theta has to be greater than or equal to 0. So if sine 2 theta is less than 0, there's no solution. So I start thinking about normally sine theta, just theta by itself is positive. I'll put it right here, positive. Let's zoom in. It's normally positive on the interval of 0 to pi. And if we've got 2 cycles, I can go around a second time, and I'll go from 2 pi to 3 pi. Now, because that's 2 theta, we want to divide out the 2. And you can see that it's only positive for theta. It's only positive from 0 to, oh my gosh, I wrote a theta. I meant pi. It's only positive from 0 to pi over 2. And then this one's only positive from pi to 3 pi over 2. So when you restrict those values and you find some points, we use symmetry. Find a couple extra points, use symmetry, and then you can see all of this information in this lemniscate. We've got the length of 3 at pi over 4. We've got -3 at, and then pi over 4 right here. We do not have anything in these quadrants because there's no solutions in those quadrants. Okay, so that's the end of your notes for today. I'm sorry, it was a little long. But go ahead and work on your assignment. Let me know if you have any questions. Have a wonderful day. Bye.